Sequences and series. Okay, so before we do anything else, we have to have two things down pat, solid. We got to know, without a doubt, what a sequence is. What is a sequence? A sequence is an ordered list of numbers. I guess it doesn't have to be numbers, but those are the ones we are going to talk about, right? So the sequences we're going to talk about are going to be a list of numbers. So an ordered list of numbers. An ordered list. Okay? As opposed to a series. What is a series? A series is where we take the elements of that list. And anyone know what we do? We add them up. We add them up. So as this gets difficult, and it does get difficult, we can never lose sight of this. These are the two foundational facts. You've got to maintain understanding of this. Okay, a sequence is the list, an ordered list of numbers. A series is when we take all those numbers and we add them together, we sum them up. Okay, so we're going to talk about sequences for a day or two here, but then series is really where we spend most of our time. So in order to talk about series, we got to know about sequences. Okay, so first of all, this is the notation. We use braces, and A sub n. A sub n. That's the notation for a sequence. And so what does that mean? So here's another way to write that. N is referring to which number in the list it is. So A1 is the first number of the sequence. 1 is referring to, it's the first one. It's the first thing in the list. A2 is the second number in the list. But 2 is referring to, it's the second one. But A2 is the actual number in the list. Okay, so A sub n is the nth term in the sequence. A sub n is the nth term in the sequence. Like I just said. Okay, here's an example. And I should have this. I should have my braces here. Uh-oh. Let's power here. There we go. All right, so I should have this. Okay, so A3 is 5. Why? That's the third number in the sequence. A6, implied by the pattern, right? Implied by the pattern would be 11. Okay? So what would A8 be? What would A8 be? Some people are saying 15. Agree with that? Yeah, it'd be 15. A sub 8 would be 15. Okay, so what about a formula that gives an? So can you come up and try, everyone work on it individually for a second. See if you can think of it yourself, because you'll have to do some problems like this. Don't just tell the person next to you once you get it. Everyone think about it. But in terms of n, right? So what, if you, could you come up with an expression dependent on n that gives you the nth term in the sequence? So one thing that helps is to make a little table so you can see. So do a, n, and n. If you don't need to do this, that's fine. But if you're having difficulty, this is helpful. So n, when n is 1, a sub n is 1. When n is 2, 3. The third term of the sequence is 5, etc. And so then, and maybe these ones for larger n make it easier to see the pattern. And so what formula dealing with n, or what expression of n, would give you a sub n? So if you plugged in n, it would tell you what the a sub n term is. That's what we're saying. And many of you have it already. Okay, what were you going to say? Okay, yeah, so you should have gotten 2n minus 1. So this is always, the a sub n term is always 1 less than twice n, right? So 6 times 2 is 12, 5 times 2 is 10. Okay, so most of the sequences we'll deal with will have a pattern, right? It will have a pattern that you can describe that pattern with a formula in terms of n, in terms of which term in the sequence it is. Make sense? Okay, harder. So let's practice. So with these, you notice that they're fractions. So what I suggest is work on the numerator and the denominator separately. Work on them as each as their own individual little expression of n. And again, I recommend make the table, right? Make the table so you can see n right next to its corresponding term of the sequence. As you notice here, it doesn't have to be a sub n. It can be anything. So I'm showing you some other possibilities. C sub n, b sub n. Okay? So everyone, these are harder. Work on them by yourself. And then if you're stuck, then get help. But try to do as much as you can by yourself. Okay, here's the hint for the first one. Notice. This is what you have to notice for this one. All right? In terms of the denominator, anyway. So can you make them all like that? If you make them all like that, then that will help with the numerator. So make all of them like that, right? Do you see? So right, we want 2 to be what? Some number of, what do we want in the denominator? What do we want in the denominator for 2? 4, right? And what do we want in the denominator for this one? 6, right? So because we see this pattern where the denominator is just, it looks like it's just n. But then some of them aren't that, like the even ends aren't like that. So let's change them. So how many fourths is 2? 8, right? 2 is 8 over 4. And now you're going to form a new sequence of numerators that's going to actually be something you can see. And the denominator is simply what? N, right? Okay, so how many sixths is 16 over 3? 32, right? How about 1? We want how many halves that is, right? And then 1 over 1. Okay, so 7 gives us 64. 6 gives us 32. 5 gives us 16. 3 gives us 8, right? 4 gives us 8. So, can you see that? So again, let's rewrite them here. So what are these? 4, so you look at the pattern. 4, 8, 16. What are those? 32. We should recognize what those are. 4, 8, so then this is 2 over 2. Yeah, 2, 4, 8, 16, 32, 64. What are those? Thank you. They're powers of 2, right? They're powers of 2. What power of 2 is this? 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, etc. So how do we use n to get this number, right? So if this is 2 to the 5th and n is 6, this is 2 to the 6th and n is 7. 2 to the n minus 1. Anybody get it before I started writing it? A couple, okay? Yeah, handful. Good. All right, this one. How about Bn? All right, so what about the... So there's kind of 3 aspects to this. We've got a numerator and denominator, and then the fact that they change negative and positive. And we can work on those all separately. So let's pretend the negatives aren't there for now, okay? We can pretend the negatives aren't there. Now we got 1 gives me 3, 2 gives me 5. So there's 3, 5, 7, 9, 11. And that's kind of like the last one we had, right? What was it, 2n minus 1? Is this 2n minus 1? No, not quite. It's kind of like it, but it's not, because 2n minus 1 would have been 1, 3, 5, 7. So how can we adjust that? 2n minus 2? Okay, that would be one way to do it. Yeah, so that works. But yeah, so if we do 2n, think of what 2n, how does each one of these relate to 2 times n? It's not minus 1 now, but plus 1. And if you simplified what you said, you get 2n plus 1, whoever said that. Yeah, so if you multiply by 2 now and you're adding 1, right? Okay, denominator. So what are these? 4, 9, 16, 25, 36. What are those? Not powers of 2, but those are squares. So what this is? 2 squared, 3 squared, 4 squared. So looking back at n, we're going to need n plus 1 squared. All right, now the fact that it alternates. This is called alternating sequence because it's negative, positive, negative, positive. So we need some kind of mathematical device that's going to give us a negative whenever n is odd and a positive whenever n is even. That's what's happening here, right? So what will that be? Okay, so if you keep multiplying negative 1 by itself, we get that flip-flopping thing, right? We get the negative, positive, negative, positive. Take negative 1 to the n. This is probably the simplest way to do this. What does this say? So when n is 1, we multiply negative 1 by itself 1 time, and we get negative. Is that what we want? Yeah, and then when n is 2, it's negative 1 times negative 1, which is positive 1. And then so whenever it's even, you have an even number of negative 1s multiplied together, you're going to get positive. Whenever it's odd, you'll have an odd number of negative 1s multiplied together, it'll be negative. So that's this. This brings me to a really important point. What is the meaning of, say, w to the n? How could you describe what w to the n is? This is going to be really important. And what I found is if you have trouble looking at that and imagining exactly what that is, then when you have all these lots of algebra and problems that involve this are more difficult. How can you describe, or what does that mean, W to the N? Yeah, to a power. What is that? To a power. What does that mean?
Kind of like multiplying W by itself an N number of times.
Yeah, so lots of you were saying it, and then he put it all together. Multiplying W times itself, what? N number of times. W times W times W times, etc. times W, and then we could say what? N W's. It's really important, and what I found is if you don't look at that and recognize and think about it that way, imagine that. Then when we come to lots of algebraic situations where we're simplifying these and we're combining these, you get lost if you can't imagine that. Okay, so this is what is this? This is saying multiply -1 together n number of times, and when you do that, whenever n is even, you get +1. Whenever n is odd, you're going to get -1, and that does exactly what we need. What's another way to do it? Anyone have another way to get these signs to alternate? Oh, good. Okay, so yeah, so if you think about trigonometry is the functions that are cyclical, right? Repetitive. So how can we get... So think about what? On the unit circle, easier it would be to think about x coordinates on the unit circle, right? X is 1, then -1. Then x is 1, and then -1 on the unit circle, right? What function gives us the x coordinate, or the horizontal distance on the unit circle? Cosine, right? And so then these would be cosine multiples of what angle? Going around, so every time we go around halfway, pi, right? So cosine of, does this work? So when n is 1, we get the cosine of pi. And that's on the left side of the circle. The x-coordinate is -1. When n is 2, cosine of 2 pi, that's over here on the right side of the circle. We get +1. So any odd number of pi's takes us to the left side of the unit circle where x is -1. That's the cosine. Right? The cosine is the x-coordinate. Any even number of pi's takes us to the right side of the circle where cosine is positive. So I think it works. So there's another way to do it. Both of those would be right. So that would give us the alternating effect, or -1 to the n. Now what if we wanted the odds to be positive and the evens to be negative? What if we wanted the odds to be all the positive terms and the evens to be negative? Yeah, so then you could do like n+1, right? If you change these n's to n+1, then it would shift it, right? It would shift it over, and all your odd ones would have an even number of negatives multiplied together, and then all the odd ones would have, or all the even numbers would have an odd number of n's multiplied together. So if we want to shift the alternating, we can do n+1. Okay, questions about these examples? Okay, so then we talk about a sequence is convergent or not. Let's write out these again. So what was Cn? Cn was 2 to the n -1 or +1? -1 over n. And then this one was, and we had an before, we had what? 2n -1. So here's the threes we've looked at so far. N, 2n plus 1 over. Did I get those right? Yep, okay. So convergence. So what we mean by convergent sequence is we look at this list of values and we ask the question, is it heading towards honing in on a particular value? Okay? So are the terms of the sequence getting closer and closer and closer, and in fact, as close as you want, eventually, infinitely close, to a particular value? What is that mathematical principle that I'm talking about? Getting closer and closer, right? That's a limit. So sequence, say, A sub n is convergent if the limit as n gets really, really big of the terms exists. Or we say equals some finite number L. That's or. It's the word or. If anything else happens, the sequence is divergent. Okay? If anything else happens, the sequence we call divergent. So what else could happen? Besides these terms getting as close as you want, getting closer and closer to a particular value, what else could happen in the sequence? Okay, so so they just get really, really big, infinitely, or just get very, very large and exceedingly large, or exceedingly large and negative. What else could happen that's not the terms converging in on one particular value? What's that? Yeah, so it could like alternate. It could kind of like the even terms could hone in on one number, and the odd terms could hone in on another number. That's a divergent sequence. Okay, that's divergent. The only way a sequence is convergent is if the numbers are getting very, very close to, and in fact, as close as you want, as long as you take enough terms out, to a one particular value. Okay, so let's look at these. What about 2n minus 1? Is that convergent or not? What was that? That was our 1, 3, 5, 7. Convergent or divergent? Divergent. These numbers just get as big as, just get exceedingly large. Just keeping it larger and larger and larger. Okay? What about 2 to the n minus 1 over n? Can we make heads or tails of that? So we got to look at, so here we can just kind of analyze these numbers. 16 fifths is about 3. 16 thirds is like 5 and some change, right? 64 sevenths. So what's happening to these numbers? They're getting large, okay? Just like the last one. So they're getting also as big as you want. They're just keep getting larger and larger. So Cn divergent. What about this one? Bn. So this is about a half, a little more than a half, a little less than a half, but negative. Now we're looking at close to a third. This is like negative a fourth. So what we can do is we can think about these as, so we can think of sequences as functions, right? We can think of sequences as functions. And what we had as a continuous variable before is now n, okay? And then what used to be our y-coordinate would be our sum of the series, right? So this is like what you're used to, x. But it's not continuous, right? It's just 1, 2, 3, 4. We're only going to get, instead of a continuous curve or line, we're going to get what? Individual points at just natural numbers, right? 1, 2, 3, 4, 5, 6. So at 1, we got what? So let's do here 1 like this. Negative 1 down here. So we can, and like a function, we can make a graph of it. Okay, so 1 was negative 3/4. 2 is 5/9. That's a little bit more than a half. So you can think of these sequences as discrete functions. Discrete functions meaning a set of points, a set of points that are not continuous, right? Not continuous. -7/16, what, a little bit less than -1/2? 9/25, that's close to a third, a little bit more than a third. -11/36, yeah. So what's happening here? So we're alternating, but the positive ones are going to get small, very close to 0. The negative ones are going to get small, close to 0. So, convergent or not? Is this sequence heading to a particular value? Yeah, even though it's alternating, both sides of it are going to get really, really close to 0. So if we came out to n was 1,000,000, what, n was 1,000,000, we'd have a really, really small positive number. And then n equals 1,000,001, it'd be a really, really small negative number. So this is convergent to 0. So because the limit as n goes to infinity of Pn equals 0. And what does this mean? It means pick any distance from 0 that you want, as small as you want. You can find an n, you can eventually find an n where your terms will all be within that distance of 0. That's really the meaning of the limit. So pick 1/1,000,000th, right? 1/1,000,000th. Is there an n so that for all n's greater than that, our terms of the sequence are within 1/1,000,000th of 0? Yeah, so it always keeps getting closer to 0. Now pick 1/1,000,000,000th or 1/120,000,000,000th. Some of you know why I picked that number. 1/120,000,000,000,000th. Okay? Is there eventually, will you get to an n where all the points after that are within 1/120,000,000,000th of from 0? And yes, that's true. It would happen. That's the meaning of the limit being 0. Okay, questions on that? Okay, so we've kind of started talking about this already. So here's one. So here's a sequence, 1/n². Okay, go ahead and when you see that, you think what? Write out what you, so you see that, think what? Write it out. See that? What is that representing? Write it out. Everyone write it out. Okay, what is a sequence? Sequence is what is a sequence? An ordered list of numbers. What's this ordered list? 1, 1/4, 1/9, etc. Okay, so when you see something like 1/n², this is what that means. And so, see this? You immediately think this. Or else this is all pointless. This is all just pushing symbols around without any meaning, okay? Okay, so what function would we compare this to? Yeah, so this is the sequence whose function would be f of x equals 1 over x squared. N is kind of like the independent variable of the function, and then the terms of the sequence, the 1 over n squared terms, are analogous to what values of the dependent variable. Okay, so how are these the same and how are they different? So let's do different first. How are they different?
X not just includes all numbers.
Okay, right. So here the implication is that x is a continuous variable, right? X is a continuous variable. You could consider all real numbers here, whereas n, we only consider the natural numbers, the positive whole numbers, right? All the natural numbers. We start with 1, 2, 3, 4. Okay, so then graphically, what would that look like? So here, if we had n and whatever our sequence is, we'd have 1, 1, 2, 1/4, 3, 1/9, 4, 1/16, etc. Is this convergent or divergent sequence? Convergent to 0. These are just numbers going to get very, very small. Okay. And so then, what about the graph of 1 over x squared? So at the whole values of x, or at the natural values of x, you're going to have the same values of the function. So how do we express that? We would say that right? F of n. So f of n would equal. So if this is a, say this is a n. So f of n would equal a n. So this is, those values are the same, but we have all for the x. When for the function x, we have everything in between. All right. So what does this look like? It looks like this. And then we even have the negatives too, right? When x is negative, we get the same thing reflected, or supposed to be. So here's f, and then this is a sub n. Okay. So how are they different? They're different because that's a set of discrete points, right? And then this is a continuous function, except at 0. There's a break at the asymptote there. But in general, we've got continuous function, all right? How are they the same? This is the key principle we were just talking about. So what's the same about them? What about this function? Looking at large values of x. It also converges to 0, right? So what's the same is the limit as n goes to infinity of an is equal to what? The limit as x approaches infinity of the function. So their convergence for large values is going to be the same. If the sequence converges, well, I should say it the other way around. So we're going to use this fact to help us decide convergence of what? Convergence of sequences. Use the associated function to determine convergence, divergence of the sequence. Okay, there'll be a web work for Wednesday, and we will pick it up there.